Okay, so let's continue on routing in the internet that we use. These are the popular routing algorithms that we use in the internet, which are RIP, OSPF, and BGP. So first of all, we have the intra-AS routing that we use within the AS, also known as Interior Gateway Protocols, IGP. So the following are the most popular intra-AS routing protocols. RIP, Routing Information Protocol. OSPF stands for Open Shortest Path First. IGRP, Interior Gateway Routing Protocol, which is a proprietary protocol of Cisco. So let's start with the RIP first, Routing Information Protocol. That is one of the oldest one, which is included in the Unix distribution in 1982. It's based on the distance factor algorithm that we just learned. So the distance metric in this case is number of hops, which can be 15 hops, and each link has a cost of 1. And the distance factors DVs exchange with neighbors every 30 seconds in response message, also known as advertisement. So in each advertisement, it can have a list of up to 25 destination subnets in IP address, of course. So this is an example from router A to destination subnets. And then the subnet U, for instance, can be reached from A. And the subnet V, as you see, can reach from A through 2 hops, 1, 2. And the subnet W also can reach through 2 hops, 1 and 2, and so on. So let's give an RIP example. We have a network topology which has some number of routers, in this case A, B, C, D, right? And we are considering the router D in this case. This is the routing table in router D. And we have 3 columns, which is the destination subnet, next router, and the 3rd column is the number of hops to reach to destination. So this red one are the destination subnet, which is W, X, Y, and Z. For instance, for the D, this is a table for the router D. The destination subnet Z can be reached through the next router is B, and we can reach to that subnet Z after 7 hops, okay, and so on. So this information can also change, and we need to update this information. So assuming that router A advertise a new information to D, for instance. So in this case, we have some information that can affect the router D, which is the destination Z, as you see from here. Destination Z can be reached through the router C with the 4 hops, compared to the current situation where the subnet Z can be reached through the router B after 7 hops. So we need to, this is a least cost compared to the current case, so it's a last cost. So that's why we need to update this one. So we need to update this information with this new information. So the Z can be reached through the A, because the next router is A for the D, and number of hops 5 instead of 7, because 1 plus 4 is equal to 5. So this way we update the routing table in router D if you receive a a change from the neighbor routers. So what happened if a link fail or we recover a link? So what are the rules of this protocol? If no advertisement, if heard after 180 seconds, which is about 3 minutes, so the neighbor link declared as a dead. So we listen this advertisement. If we don't hear an advertisement from a node after 180 seconds, well, then we consider this link or neighbor is a dead. So if any change happen or new advertisement sent to the neighbors response to this change, new advertisements, if tables change, of course. Link failure information propagate quickly to the entire networks. So if a link is failed, this information can propagate very fast to the entire network. And we have some problem like poison reverse, which is used to prevent ping pong loops. How do we process the RIP table? First of all, these RIP routing tables are managed by the application level. Remember, application level process called route D or daemon. So the process in the application layer, which is called route D or known as daemon, it manages this forwarding table in the RIP. So the advertisements sent in UDP packets in the transport protocol, remember, and periodically repeated. That was the first intra-AS routing algorithm. Intra-AS means the routing within an autonomous system. The second one is the OSPF, stands for Open Shortest Path First. Open because it's a publicly available, it's not a private protocol. And it uses the link state algorithm. Remember, the RIP utilizes the distance factor that only advertise or exchange information with neighbors. But in the link state, all the nodes receive the same information. So in this case, in the link state algorithm, remember the LS packets are disseminated, and we have the complete network topology in each node, and the routes, the paths are computed using the Dijkstra algorithm that we just learned in the previous lecture. And another important point that OSPF advertisement, they carries one entry per neighbor, and the advertisements are flooded to the entire, the whole AS. And then these OSPF messages directly are carried over the IP, not TCP or UDP. And there is another very popular algorithm is called ISIS routing, and which is nearly similar to the OSPF protocol. So OSPF has some more advanced feature compared to the IRP in terms of security. First of all the OSPF messages are authenticated. Why? In order to prevent the malicious intrusions. And we have the multiple same cause paths allowed. Compared to the IRP, only one path in IRP is allowed. Here, we allow multiple same cost. For each link, multiple cost matrix for different type of service. So we have a type of service. For instance, for the set line, link cost can be set to low for best effort TOS and high for real-time type of service. And then another feature, integrated uni and multicast support. Multicast OSPF MOSP uses the same topology database like OSPF. And hierarchical OSPF is used in the large domains. Let's look at the hierarchical OSPF. We have 4 different routers. And first of all, 2-level hierarchy. We split this network into 2 parts. This blue part is called backbone, and the remaining part is called local area. In the local area, we have area 1, area 2, area 3 in this case. And there are the type of the routers that we use in this case is called internal routers. And each area that is managed by the area border routers, as you see. And these area borders are connected to the backbone router. And the backbone router are connected to the boundary router. As you see, we have hierarchy. So in this hierarchy, we said that we split the hierarchy into 2 parts, local area and backbone. And link state advertisement only in area, the bottom area, these areas. And each node has detailed area topology, only know the direction to the networks in other areas. And the area border routers, it summarizes the distance to networks in own area and advertise to other area border routers. So in each area 1, we have these area border routers. In area 2, we have these area borders, and so on. So these area borders, they summarize this information and convey to the other area border routers. And then we have the backbone routers, where we run the OSPF routing limited to the backbone only. And the last one at the top of this hierarchy, we have the boundary router that communicate with other AS, autonomous system. This is how we implement the hierarchical OSPF. Now, let's look at the inter-AS routing. So far, we consider the intra-AS, the routing information within a single autonomous system. Now, what are the protocols that we use for the inter-AS between AS? So it's called BGP, and it stands for Border Gateway Protocol. This is the de facto interdomain routing protocol. In other words, it holds the internet together because it communicates multiple AS. So in other words, it keeps together the internet. So BGP protocol, it provides each AS the following using the following information and the protocol. So we have 2 types of BGP. The first one is called eBGP, external BGP, which obtain the subnet reachability information from neighboring AS. So it obtained the reachability information from the other AS, neighboring AS. iBGP, as its name implies, is the internal BGP. It propagates this reachability information to all routers in the AS. Then BGP also determines the good routes to other networks based on this reachability information and the policy. Policy is also important. And it also allows subnet to advertise its existence to the rest of the internet by saying that I am here. So let's look at this BGP basics, which we call BGP session. So what's the BGP session is the session between two BGP routers to exchange the BGP messages. Advertising paths to different destination network prefixes. So as you see, when AS3 in this case advertises a prefix to AS1 using the BGP session, and AS3 promises it will forward datagrams towards that prefix. AS3 can aggregate prefixes in its advertisements. How do we distribute the path information? Remember that, guys, we said that we have two types of BGP session. The first one is eBGP session with the solid line between AS3, AS1, and AS2 and AS1 is an inter-AS session. And iBGP, which is the dashed line, we use this protocol, this session within the AS, a single AS. So, for instance, using the eBGP session between 3A gateway and 1C gateway, AS3 is going to send prefix reachability information to AS1. So the AS3 is going to send this prefix reachability information to AS1. Then 1C gateway, then use iBGP session in order to distribute this new prefix information to all the routers in AS1. In this example, 1A, 1D, 1B. So the 1C get this reachability information and distribute among the other routers in the AS1. 1B can then re-advertise new reachability information to AS2 over 1B to 2A eBGP session. Okay. And this 1B also, it received this reachability information from 1C, and then it's gonna re-advertise this reachability information to the 2A gateway in the AS2. So when router learns new prefix, it creates entry for prefix in its forwarding table. Okay, what's the path attributes and BGP routes? So we talk about the advertisement prefix. So what's the route? Route is equal to prefix plus the attributes. So two important attributes in the BGP. The first one is AS path, autonomous system path. It contains the autonomous through which prefix advertisement has passed. So it contains the number, the AS number that this prefix advertisement has passed through so far. And then the next important attribute is the next hop. It indicates the specific internal AS router to next hop AS. Okay. So here, of course, the reachability information is important, but at this level, the import policy is very important also. Even though the gateway router receives some route advertisement, and it uses the policy to accept or decline this advertisement. For instance, you can put a rule that never accept route through or advertisement from this AS X, for instance. Any message or any advertisement that comes from this AX, don't accept. So you can put such policy, which is a policy-based routing. How the BGP select the route is based on the following steps. So we may have multiple, kind of paths or routes to the destination, but we're gonna select one of them. So in the first step, policy decision, then the shortest path, shortest AS path, and then closest next hop router using the hot potato routing method and some additional criteria. These are the four main criteria that is used by the BGP in order to choose a route. These are some details that I'm skipping. So, this figure from the previous slides as well, how an entry get in the forwarding table. This is a prefix 138.16.64/22. According to the forwarding table, if you receive such prefix entry, you're gonna move this to the output port of number 3. So how a route looks like in this BGP? Let's look at it. First of all, we talk about the BGP message, which we call external BGP, eBGP message between AS. So the BGP message, they contains the route information that is given as an example here. This is a sample route information in the BGP message. So as you remember, route was equal to the prefix plus the attributes. Prefix is usually it consists of the IP address and related to subnet mask and so on. And the attribute is the AS path. Remember what was the AS path? In this case is AS3 and AS131. That means this advertisement or prefix is passed through this AS3 and AS131 so far. It passed through these two AS and reached to this point. What's the next hop? Is this IP address. So the prefix plus these attributes is equal to the route information in the BGP message. There's some detail I'm skipping. So remember we said how we're gonna select the best BGP route. We mentioned about 4 criteria. One of them was, remembered, router selection was based on the shortest autonomous path. For instance, if you have 2 paths, one of path has this attribute, which is AS2, AS17, and the other one has a AS3, AS131, AS201. So that means this message is passed through only 2 AS. In this case, this message is passed through 3 AS. So because this 2 is less than 3, we select this router. So it's based on shortest AS path. And so on. So find the best intra route to BGP route. So we use the selected route's next hop attribute. Route's next hop attribute is the IP address of the router interface that begin with AS path. So next hop attribute is the IP address. In this case, so the router uses OSPF to find the shortest path from 1C gateway to 2A, which has this IP address. So this is how we select the best intra route, and so on. So, in summary, how does entry get in forwarding table? First of all, the router becomes aware of prefix through the BGP route advertisement from the other routers. And then based on this, it looks at the router outputs port based on the prefix. It determines the output port. And here we have different criteria, remember. We use the BGP route selection to find the best inter-AS route. And we use the OSPF to find the best intra-AS route. And then the router is going to identify the router port for that best route. And then we enter this prefix port entry into the forwarding table. Okay, so we talk about BGP and we said not only the attributes, the route information, also the policy is very important. When we route, message from one point to another point. So BGP routing policies is very important. So let's give an example. Here we have 3 ISP, Internet Service Provider networks, A, B, C, your Internet Service Provider. And let's say we have 3 customers, X, W, and Y. And in this case, X is a dual homed. That means it received the service from 2 different companies. So the policy says that X doesn't want to route from B to C. So X doesn't want to route traffic, network traffic. It doesn't want to, carry the traffic from B to C. So X will not advertise to B a route to C. This is one of the policy, for instance. You can put such rule. So A advertises paths AW to B, okay. B advertises path BAW to X, which is okay. Should B advertise path BAW to C? No, because B gets no revenue, no money for routing the CBAW path. Why? Because neither W nor C are B's customer. So why should carry such, traffic over itself? So B wants to force C to route to W via A. So B forced the C to route the traffic to W through A. So B wants to route only to its customer, of course. I'm the company, so I want to just, serve to my only customer, not the other company's customer. So that's why I wrote only to and from my customers. So these are the policy. When you admin and manage a routing at the high level, you can put such policy and rules. Then why different intra and inter-AS routing? The policy play very important role here in case of inter-AS, because admin wants to control over how its traffic is routed and who routes through its network. Of course, I want to control what kind of traffic is I'm carrying and who I'm going to route this network traffic. But intra-AS, in intra-AS, you have a single domain admin. So in the intra-AS, since you are the only admin, then there is no need for the policy. But intra-AS, so you have a neighbor companies and their network. So we need a policy, how to exchange, how to manage, how to share this traffic basically. The scalability, because putting this hierarchical routing is going to save the table size and it reduce the update traffic. So it's going to be practical. In terms of performance wise, let's look at the intra-AS within an AS. The most important thing is the performance. So I focus on the performance of my network. But when it comes to the inter-AS, here the policy may dominate over the performance. So the policy may become more important than the performance, because if you select a wrong policy, then your performance may degrade. You know, you may have a poor performance or low performance. So that's why you have to select your policy and rules very carefully. Okay, so that was about the most common intra and inter-AS routing that we use in the current internet architecture, which was RIP, OSPF, and BGP. So far, we talk about the unicast routing, so means routing from one point to another point. What about broadcast and multicast routing? How do we achieve this? Broadcast, as you know, is from point to multi-point, and multicast is from point to a set of group, right? How do we achieve this broadcast and multicast routing? So let's look at the first broadcast routing problem. Our main objective here is to deliver packets from one source to nodes, broadcast. So there are two approaches in this case. The first one is called source duplication. The second one is called in-network duplication. As you see from the figure, you start the duplicate information at the source, which is not efficient, not practical, you know, because you're generating unnecessary a copy of information, multiple copy of information. But in network, the application is more efficient and more practical. So that's why we're going to focus on the in-network application. So what are there are three main methods in this case. It's called flooding. The first one is called flooding. So what's the flooding? When node receives broadcast packet, it sends copy to all neighbors. Okay. But what's the problem here? We may, you know, end up with the cycle, loops, and the broadcast storm, because you have a single piece of information and you're, you know, duplicating this, and you're making multiple copies of the same information, and you send all these copies to all your neighbors. So the second method, in order to address some of the issues of the flooding, is called controlled flooding. So node is I'm a node in the network. If I receive a packet, I'm gonna broadcast only the packet that if it's not has broadcasted before. How am I gonna know that I haven't broadcast this same packet before? Then I need to keep track of the packet ID, right? So I look at the packet ID. I receive a packet ID. If compare with my state information, the previously broadcasted packet IDs. If this is a new packet, then I broadcast, otherwise I discard. So therefore, each node needs to keep track of the packet ID that already broadcasted. Or reverse path forwarding is another solution, RPF. Only for the packet if it arrived from the shortest path between node and source. If I receive the packet only from this shortest path, then I'm gonna forward that packet. And the third most common method is called spanning tree. So this actually solves many problems. So we don't receive any redundant packets by any nodes when we broadcast. Okay, so spanning tree. First of all, in the first step, we're gonna construct spanning tree, and then based on this, by using this spanning tree, we are gonna the nodes within this tree is gonna forward and make copies along only this tree. For instance, in the left side, we have a broadcast that initiated at node A, and we have a broadcast initiated at D. We said that in the spanning tree method, the first step is to construct the tree. In this construction of the tree, the first of all, we need to, in the first step, we need to select a center node. So, for instance, in this example, the center node is selected to be node E, this one. And then each node, after selecting the center node, each node is going to send unicast join message to center node. Sorry. First, assume that the node F send a unicast message to center node, which is node E, in order to join to the tree. Okay. Then the B send a unicast join message. Then A, and for node C, then node G. So we construct this way. So when we construct this tree, the message is forwarded until it arrives at a node already belonging to the spanning tree. For instance, in this case, the A send a unicast join message, but it's gonna hit to the node B. So that's why I add this link to between A and B to the tree. And then C. In case of G, as you see, it's gonna hit to the node D that is already belong to a spanning tree. By using this unicast join message, I construct the spanning tree. That was about the broadcast. Let's talk about the multicast routing and try to define the problem first. What we are trying to do, what's our goal? What's our goal is in multicast routing, we are trying to find a tree or trees that connecting routers for a set of nodes, okay, not all the nodes. In the broadcast, we broadcast the message, we forward the message to the whole nodes. But here we are gonna forward this message to only a group of a set of nodes, which we call multicast. Here we have different tree structure. The shared tree on the left, as you see, is the same tree used by all the group members. So when you say group member, are the multicast group member, which is coded with the red color. So these are the group member client. The black one are the not group member, because it's a mix. In your multicast, some of the nodes are your group members, some of them are not your group members. So in our case, the red color node are our members, the black color are not our members. Similarly, the router we can classify into two, group member router and not group member router. So as you see in the shared tree, we have a same tree that is used by all the group members that connect all these group members. And we have a source-based trees, which is another approach, different tree from each sender to receivers. For each source, we come up with a different tree, basically. If this is the source, you see the blue tree. If this router is a source, then we use a green color tree. So there are several approaches, a couple of approaches for building multicast trees. The first one is called source-based tree. That means one tree per source. In this case, we have two popular methods, which is called shortest path trees and reverse path forwarding. We have a group shared tree. That group use only one tree that I show you. In this case, we have two methods. The first one is minimal spanning or Steiner method. The second one is center-based trees. We're going to first look at these basic approaches, then talk about some practical protocols that we use in the current internet environment. So let's start with the source-based tree. So multicast forwarding tree. In this case, there is a tree that shortest path routes from source to the all receivers. So how do we find the shortest path in this case? In this method, we use the Dijkstra algorithm that we just learned in the previous lecture, guys. So assume that R1 in this case is the source, and then we use the Dijkstra algorithm as a source to construct the tree, shortest path. So we use the Dijkstra algorithm to construct the shortest path routes. So this number indicates the order link that is added by algorithm. So first we add this path, then this, then third, then fourth, then fifth, and then sixth. So the second method we said reverse path forwarding. It relies on router's knowledge of unicast shortest path from it to sender. Each router has this. Each router is gonna use the following criteria. Okay. It behave as follows. If the multicast datagram received on the incoming link on the shortest path back to center. If I receive the packet from this red path, which is the shortest path tree, then I'm gonna multicast. I'm gonna float the datagram all outgoing links. And otherwise else I'm gonna ignore or discard this datagram. I'm not gonna forward. So the reverse path forwarding, it works with this simple behavior. If I receive a datagram, if datagram comes from number of 5 links, so let's how can I say? Let's give it an example. This router 5, right? Okay, let's talk about router 7. Okay, router 5. No, let's talk about router 6. So I am the router 6 now, or 6. I receive datagram from paths 4. which belongs to this path belongs to the shortest path tree, right? Then I'm gonna float to all the outgoing links to R3, for instance. But if I receive a datagram from this from R5, black link, then I'm not gonna flow. I'm gonna discard this, ignore this datagram. This is how the reverse path forwarding works. There's an example here also. As you see, the red colored are the group member, multicast group member. The blue one are not group member. So this is the shortest path tree that we constructed using the Dijkstra algorithm. So as you see, with this red arrow, the datagram will be forwarded, right? It will be forwarded, but the datagram will not be forwarded for this black link, okay? So the result is a source-specific reverse spanning tree. Okay, there's another method, kind of method in the RPF, which we call pruning. So we construct this shortest path tree, but the forwarding tree may contain some subtrees that is not member of the multicast group. So therefore, we don't need to forward datagrams to this down subtree that are not my group member. So that's why I need to prune, cut these subtree branches. This process is called pruning, cutting the branch from a tree. So that's why I send a prune message, sent upstream by the router with no downstream group members. So for instance, R7 doesn't have any group member, right? Is not a red one. That's why we need to cut this branch. So R7 is gonna send prune message to R5, okay? And then R5 is gonna send this to upstream, and then we're gonna cut this branch because R7 doesn't have any group member, so that's why I don't need to forward message to this subtree. So we need to cut, which we call pruning. Okay, that was about source-based tree. So one source. And the second approach, group uses only one tree, group shared tree. So one of the method here is called Steiner tree or shared tree. So minimum cost tree connecting all routers with attached group members. And this is a NP complete problem, of course. And there are, of course, a very good heuristic solution, but not used in practice because it's computationally very complex. Information about the entire network is needed and is a monolithic, so you need to rerun whenever a router needs to join or leave. So because of this, is not practical. So let's look at the center-based trees. In this case, there's a single delivery tree shared by all the nodes. In this case, in this method, we have a one router that is identified as the center of the tree. How to join to this tree is edge router sends unicast join message that is addressed to the center router. And then this join message is processed by the intermediate routers and it's forwarded towards the center to make a decision. So join message either hits the existing tree branch for this center or arrives at the center. So the path taken by join message becomes new branch of tree for this router. and this branch is added to the tree. Suppose, let's give an example. Assume that R6 in this network is selected to be center. So R3 send a join message, unicast message in the first step, and then R4 send a join message, and then R1 send a join message to R4. With this way, we constructed tree. Okay, some of the popular broadcast and multicasting routing in internet environment is DVMRP, which stands for Distance Vector Multicast Routing Protocol, RFC 1075. This protocol has a flawed and prune feature by using the reverse path forwarding and source-based tree method. You know, the reverse path forwarding tree, it was based on DVMRP's own routing tables that is constructed by also the DVMRP routers. There's no assumption about the underlying unicast. So initial datagram to the multicast group member flooded everywhere using the RPF method. So if there's any unwanted group member, then we send upstream prune message to cut that, branch. So it has a pruning mechanism basically. Soft state. So this protocol router periodically forgets about the branch that are pruned, that are cut every 1 minute. So that means that branch automatically join or is available to join. So the multicast data again flows downstream to unpruned branch, and the downstream router, they're responsible for reprune or else continue to receive data. So this DVMRP is usually used in the commercial router, is a practical protocol. So another issue is the tunneling. The question is, in the real network, in the internet, we have the, unicast routers, but using this unicast routers infrastructure, I'm going to send a multicast message. So how am I going to connect this group of multicast routers within the unicast router networks, as you see from here? This is the actual case, the practical case. In order to reach this multicast group member, I need to go over these non-group member unicast routers. So my logical topology looks like this, but this is not the practical case. In realistic case, this is the physical topology. So how am I going to solve this problem? Is encapsulation. So the multicast datagram is encapsulated inside normal datagram, like a non-multicast address datagram. We encapsulate, and the normal IP datagram sent through the tunnel via regular IP unicast using the IP unicast protocol to receiving multicast router. This tunneling is resembles to the IP version 6, IP version 4 tunneling, if you remember. It works in similar mechanism. Then the receiving multicast router will receive this IP unicast and unencapsulate to get the multicast datagram. So of course there are other practical protocols which we call PIM, protocol independent multicast. It doesn't depend on any specific underlying unicast routing algorithm. It works with all. There are details of this. I'm skipping. Okay, that's the end of the chapter of the network layer. So remember, in the previous weeks, we start with the introduction. We compare the virtual circuit and datagram networks. And then we introduce the router architecture. What's inside the router, how it looks like. And then we move to the IP protocol, Internet protocol, by mentioning the datagram format, their version, IP version 4, how do we solve the addressing issues, and how we control and manage this protocol. And we talk about IP version 6 transition. And this week, we cover the routing algorithms by first talking about the main approaches, which were link state and distance vector, as well as the hierarchical routing. After these principles, so we study the popular intra-AS and inter-AS protocol that we use in the internet environments, which are RIP, OSPF, and BGP. And last but not least, we talk about the broadcast and multicast routing, how to achieve this type of routing and the methods that are used, and the most popular protocols that we use for the broadcast and multicast routing.